In this tutorial, we're not covering MPI plus hybrid or threads because I think you are really going to have a presentation this afternoon on MPI plus OpenMP. So I will just focus here on MPI plus accelerators, which is basically mixing different programming models used for accelerators. I will also not focus on any specific programming model for accelerators, but I will try to give you like the broad picture and some basic concepts. So accelerators are becoming increasingly popular in parallel computing. The reason is that they are specifically designed for a data parallel execution model, in which you have basically the same operation applied to many different parts of your data domain in parallel, whereas CPUs are typically optimized for task sequential execution model, in which the focus is more on the latency. You can perform, basically you can execute a large number of tasks at a very efficiently and quickly. For this reason, CPUs have a small number of complex compute cores that allow different optimization, for example, out-of-order execution. They also have deep pipelines that reduce the maximum length of the circuitry in the chip and allow to boost the clock frequency. Large caches that minimize the impact or the penalty of accessing memory from the tasks by caching data in faster memory on chip, and also branch prediction hardware that optimizes the usage of the pipelines by reducing the number of the code fetch and decode instructions for instructions that are out in a branch that is never taken by the code. GPUs, on the other hand, have a very large number of simple compute elements that perform the same operation in parallel concurrently. They have smaller caches, shallow pipelines, and very high bandwidth memory of chip, high bandwidth memory. So ultimately, accelerators, more specifically GPUs, are very power efficient. They deliver higher flops per watt, and they also have higher flops per dollar. So people are really gaining interest into this type of devices. And this trend is also confirmed by looking at the top 500 list for which lists the top 500 supercomputer in the world. If we look at the top 10 computers in the list, we see that 5 of them use accelerators, more specifically GPUs, NVIDIA GPUs. And future upcoming Exascale system will be also leveraging some sort of acceleration technology. For example, Argonne will be hosting Aurora, which will be based on Intel-based technology for accelerators. Frontier at Oak Ridge will use whole AMD solution for both CPUs and GPUs, and China is also working on his Exascale supercomputer with a custom solution. So we see that GPUs are very well suited for fine-grained data level parallelism, in which we have our domain, we have different elements in our domain, and we can compute each single element independently using the cores in the GPU. So this model fits to the shared memory single instruction multiple data model. For programming GPUs, there are many available platforms that can be used by programmers. These sometimes are vendor specific. For example, one of the most popular programming models used for programming GPUs is CUDA from NVIDIA, which is NVIDIA specific. There are other solutions. For example, AMD also offers a programming model that is similar to CUDA called HIP. OpenMP also, as we saw yesterday, also supports Accelerator using the target directive. OpenACC is another directive-based programming model that is similar to OpenMP, but targets specifically accelerators. And I think you have a tutorial for this as well in the coming days. Then there is another programming model called OpenCL, programming model library. OpenCL is not specific to GPUs, but is more for any type of acceleration device. For example, is also used for DSPs or FPGAs. So it is more portable than other programming models. So in this presentation specifically, I won't focus on any one of these. I just want to make you aware that this exists, and if you want to get more information, there is plenty of material online that you can look for. So now we basically have classical CPU devices with their memory subsystem, and we also have GPU devices with their own memory subsystem, and they sit in the same node. So the question is, how can we move data between GPUs using MPI? And for example, we may want to move data from the GPU memory to the memory of the CPU in the same node or across the node through a network link. So how do we do that? The answer is it depends on the hardware that you have in your system, whether the MPI implementation is able to support this hardware, is aware of GPUs and the GPU library, runtime library that you are dealing with. But besides, most cases nowadays, this happens in the same way that it would happen for moving data between host CPUs. So there is pretty much almost no difference between these. And the reason is that there has been a lot of work on optimizing the data transfer between accelerators, both in the MPI community and, of course, also vendors have provided hardware solution for doing that. So one of the solutions that is provided for allowing this type of transparent communication or equivalent communication between GPU memories is called UVA. UVA stands for Unified Virtual Addressing, and is basically a memory management system supported in modern 64-bit architecture. With UVA, basically CPU and GPU can use the same pointers for referencing their physical memory. So there is no distinction between host and device pointers. And the user can query the location of the data location, so the actual physical data, where is the actual physical memory, is this on the host or the device? And that can be queried using the GPU runtime library that many MPI implementation can also take advantage of. So now we have the situation in which we have some data on one GPU memory, and we want to move this data to a GPU in a different node, for example. So if our MPI implementation is GPU aware, it can take advantage of UVA technology to query the pointer that the user passes to the MPI implementation. So you have your GPU pointer, you pass it to MPI, and MPI can query whether the physical memory for that pointer is on a host or a GPU. And if the data is on the GPU, the MPI implementation can optimize the data transfer. Excuse me. Of course, the type of optimization depends on the level of hardware support. For example, some InfiniBand cards from Mellanox support this technology called Peer Direct, which basically allows the network card to directly access the GPU memory completely bypassing the host. And this is the case for the bottom picture, the zero copy. Zero copy means that the host memory is not involved at all in the data transfer. On the other side of the spectrum, if you don't have any hardware support, you have that the MPI implementation has to transfer data through the host memory. And to do that, the MPI implementation has to allocate a buffer in the host memory, register it, pin it with the GPU so that the GPU can directly DMA data into it. And then the MPI implementation can move the data from the register buffer to another network register buffer that can be directly accessed by the network card. In the middle, there is some additional implementation that can support this type of single copy optimization. For example, GPU Direct from NVIDIA, GPU Direct version 1 supported the possibility to basically reuse the same buffer, the same GPU pin buffer also in the network. So you only need to allocate one buffer, and then you can transfer data directly from the GPU and read data directly from the network card. There is also some optimization for intranode communication that allows to bypass the host memory. This is called the GPU peer-to-peer. In the case of NVIDIA CUDA, this is supported with GPU Direct version 2. Other GPUs, also AMD GPUs, for example, support this feature, this optimization. And basically means that the GPU can directly move data between the two memories without involving the host. The host might be still involved for transferring the memory handle, because if you have, for example, let's say you have two MPI processes that are using two different GPUs in the same node, and you want to transfer the data from the GPU managed by one process to the GPU managed by the other process, the GPU pointer in one process won't make any sense for the other process. So you have to basically create a memory handle, communicate this memory handle to the other process with MPI, and then the other process on the other side can open the memory handle and launch the direct memory transfer between the GPU memories. So there is also some effort in the Linux community towards the unification of GPU and CPU memories. And this is a very interesting topic because in terms of productivity is also very difficult to program GPUs for many of the computer scientists, domain computer scientists that work with, don't have a deep knowledge of how GPU works in the specifics. So heterogeneous memory management basically is the next step towards this unification. And there is support in the Linux version 4.14 for heterogeneous memory management through helper function. So heterogeneous memory management basically means that a buffer allocated in the host can be used in the GPU as well as in the host interchangeably. The user doesn't have to do explicit data movement between the two different address spaces. The Linux kernel will take care of basically moving the data based on page faults. So this works in a similar way of basically paged memory, where you have basically pages that are moved to the swap area of a disk. when the memory gets filled, and they get swapped back in when the memory is accessed again. So in this picture on the right, for example, we have that there are some pages on the GPU memory. The CPU, if the CPU tries to access this memory, it causes a page fault. The Linux kernel basically realizes, oh, this is a page fault. The pages are on the GPU memory. It migrates the pages to the CPU and invalidates the pages on the GPU. So to support this, both CPUs and GPUs have to have a copy of the same page table. So there is some replication there, some additional details. You maybe ask some question later on. We can answer something more in detail. I think that for now, this is enough to understand the concept. So what does it mean for the MPI implementation to have heterogeneous memory management support? There are cases of, as I said, heterogeneous memory management is not is just a set of helper functions in the Linux kernel. It is still an ongoing project, so there is no definitive solution for that. But there are, in any case, programming models like CUDA, for example, that support something similar with additional restrictions called, for example, unified memory in CUDA. So if you're using unified memory in CUDA, how do you handle your program when you want to transfer data using MPI? So the MPI implementation, in theory, can work with unified memory or heterogeneous memory management transparently. However, this might not work and actually can cause problems. And there are different reasons because this can cause problems. In practice, if you are registering, if you are trying to register some memory that is managed by the system, you never know whether the physical pages for that memory, that virtual pointer, are in the GPU or the CPU. So it's difficult for the system to register them. And the system can fail because the pages, it might assume that the pages are on the host. The pages are actually on the device, so it will cause a failure. So even if it doesn't cause a failure and the pages are there, they may refer to stale data. And this can cause correctness issues if you end up accessing data that is updated maybe by the CPU at the same time. In any case, MPI, to avoid this type of problems, MPI can never work directly with heterogeneous memory and should always use a bounce buffer. So it will allocate a copy buffer in which data is transferred into before it's sent by MPI. So this is an example of how MPI can deal with heterogeneous memory management. So MPI can, for example, assume that the physical data is always on the host. Then MPI copies the data to the network pin memory if the guess is right, and it will work fine. If the guess is wrong, the access to the host memory will cause a page fault, which will cause a GPU memory migration to the host, and it's definitely ultimately more expensive in terms of latency. On the other hand, the MPI can also assume that the memory is always on the GPU. In this case, if the guess is right, MPI will do a copy directly to the bounce buffer in the host memory and transfer the data. If the guess is wrong, the access to the GPU memory will cause a page fault that will cause data to be transferred from the host memory to the GPU memory and then back to the host memory. So in general, MPI implementation should consider data to be in host memory. Is less expensive in that way. So this basically concludes the part on accelerators. I didn't give any specific introduction to any programming model from NVIDIA or AMD. These are pretty actually similar, HIP and CUDA. But if you have any questions, I can answer maybe.
There was one question from Slack. Do you have measures of any performance measurements of heterogeneous memory management you can share?
No, we don't, unfortunately. So I guess we can move to, we have a few minutes for the...
Yeah, there's only a few minutes left. So we had some hands-on examples spread throughout the presentation. Maybe you can put up...
I have the collective one, which I skipped one, yeah. Earlier on. So for the collective case, you have implemented, actually you have seen the case of stencil code using non-blocking point-to-point operations. For collective operation, you can also basically re-implement or do some changes to the base code that is in non-blocking point-to-point stencil to use all-to-all V to implement the data movement, the allo exchange. So basically, when you use all-to-all, you are using a collective operation to do the data exchange, and of course, not all the processes will need to communicate with all the other processes. So in the count vector, you will only need to specify data for those processes that require communication, and 0 for all the other processes. We have a solution for this exercise is in blocking collective stencil all-to-all V. There is also another version using non-blocking collectives that basically is in non-blocking collective stencil all-to-all W. And unlike all-to-all V, in which basically the data type that you define in the collective call is the same for all the data, in all-to-all V, you can specify different data types. So again, you don't need a pack buffer anymore. You can just use directly your source buffer and use different derived data types.